since 1992. Previous positions at RNL include leading reactor technology R&D integration, senior program manager, and lead of the reactor analysis group. He is active in the American Nuclear Society and is the current chair of the ANS Technical Journals Committee. So with this, thank you very much, Jess, and I'll let you start.
Very good. Well, thank you very much. I appreciate the opportunity to talk about the work that we're doing in CASL. I'm going to go through an overview today of CASL, and then I've got some of our researchers that will talk about the work that we're doing. As you can see on this title slide, this includes Brian Kendrick, who works in our Fuels, Materials, and Chemistry focus area, Kevin Clarno, who works in our Physics Integration focus area, and Jeffrey Secker, who works on as our Crud Challenge Problem Integrator, and I'll explain what challenge problems mean in a little bit. I'll go ahead and give a little bit of background on these folks, and then we're going to hand off the presentation as we go through, so we don't have to stop. So Brian Kendrick is a technical staff member in the theoretical division at Los Alamos National Lab. He has PhD and BS degrees in physics and engineering. For the last 22 years, his research has been focused on modeling coupled transport and chemistry of materials aging in support of the NNSA Stockpile Stewardship Program. And he's the lead code developer for the CRUD modeling effort for a code we call Mamba. So you'll hear about that. Kevin Clarno is a senior research staff member at Oak Ridge National Laboratory. He's been here for about 10 years, and his background is reactor physics, reactor analysis, and computational science. Kevin leads our physics integration focus area that you'll hear about more in a little bit. And Jeff Secker is with Westinghouse. He graduated with a BS degree in nuclear engineering from University of Illinois in 1979. He's been with Westinghouse for 36 years, working in core design, fuel development, fuel management, methods development areas. And he's been involved in modeling and evaluating CRUD, which will be one of the things that we will talk about for more than 20 years. And so we've got a good collection of researchers. So let me go ahead and move on to the next slide. So first question is, what is the Consortium for Advanced Simulation of Light Water Reactors? So CASL, as we call it, is the first DOE Energy Innovation Hub, and these hubs connect fundamental research through technology development, combining government, academia, and industry, and you're seeing some of that with the speakers today. I'll go through our membership in a minute. So our primary objective for this hub is to provide leading-edge modeling simulation capability to improve light water reactor performance. And for an outcome, what we want from this is a safer, more productive commercial nuclear power production, and use comprehensive science-based modeling simulation technology, leveraging other DOE investments and work that's been done in computing and applying it to nuclear energy. So our primary sponsor is the Department of Energy Office of Nuclear Energy. We've been going for 5 years now. We've got a 5-year award and then another 5-year renewal that we just started. And so we'll talk about some of our progress today. So you might ask what a DOE Energy Innovation Hub is. This slide talks about that. So the former DOE Energy Secretary, Stephen Chu, started this concept. And he won a Nobel Prize for work that he did at AT&T Bell Labs and thought that was a good research model where you have a integrated team going all the way from discovery to application, focused on a critical problem and combining basic and applied research. So you can see from what I talked about previously and with the organizations that we have, we're going from research and working to get this deployed. And then there are 4 hubs currently in operation. CASL was the first one, but there are 3 others. I've got their logos here: Joint Center for Artificial Photosynthesis, Joint Center for Energy Storage Research, and Critical Materials Institute. And if you want to learn more about hubs in general, you can see that link down at the bottom, or just Google Energy Innovation Hubs. I'm sure it'll be the first thing that pops up. CASL is a national laboratory industry university partnership. What's listed or shown here in this graphic is the members, what we call founding members, those that were in the original process of developing the concept of CASL back in 2010. Oak Ridge National Laboratory is the lead organization for this this consortium. We have 3 other laboratories involved: Idaho National Lab, Los Alamos National Lab, Sandia National Laboratories. We also have 3 universities as founding members: University of Michigan, NC State, MIT. And then from industry, our founding partners are TVA Westinghouse and Electric Power Research Institute. In addition to these founding members, which are the primary, where most of the technical work and other work is being done, we also have what we call contributing partners. I've got their icons here. I won't go through all of these. These are primarily single or a few PIs that are contributing to our work involved. You can see a lot of universities there. We got other vendors, Ariva, GNF. We have independent software vendors as well: CD Adapco, ASComp, Anatech. And so overall, we've got about over 200 people working on CASL right now through all of these organizations. So the scope then for CASL is to what we call develop and apply a virtual reactor to assess reactor operation and safety. So a virtual reactor, basically software simulation of the reactor, which is something we've been doing in the nuclear industry for a while, but we want to improve the predictive capability, improve the physics that's being modeled. So we're focusing on the fuel and vessel. You can see the image on the right gives an idea of what we're focusing on. For our first 5 years, we focused on PWRs. For the second 5 years, we're broadening this to boiling water reactors and light water small modular reactors. The way we're organized is in technical focus areas. You've heard 2 of those: fuels, materials, and chemistry, and physics integration. We also have focus areas on thermal-hydraulic methods, radiation transport, validation, modeling applications, and then technology deployment and outreach. So these focus areas provide the necessary physics models and physics integration. We've got an integration of these components into our virtual reactor, which is called VERA. You'll hear more about that from Kevin in a little bit, into a software system that we then can apply to address problems. And then, of course, we're working on validation to understand the uncertainties and the predictive capability. The technical scope that we're applying the software and modeling development to is what we call challenge problems. And this next slide lays out the challenge problems that we defined. These are areas that as we developed the concept of CASL back in 2010, our industry partners pointed to these as areas that could benefit from improved modeling and simulation. So, for example, and those of you are probably very familiar with this, and if you look in the upper left, pellet-clad interaction, our goal is to be able to improve the ability to predict core-wide PCI margin and for missing pellet surface PCI. Listed below is the physics areas that are involved, and you can see these align well with our organization structure focus areas as well. And you can go around this, look at the different challenge problems, cladding integrity for reactivity insertion, and also loss of coolant, so not comprehensively modeling the full event. And then also other ones: departure from nucleate boiling, grid to rod fretting. What we're going to do today, rather than talk about each of these in detail, we're going to focus on one of them, the one I didn't mention, Crud, and go through that as far as the fundamental work that we're doing, the integration that we're doing, and results that we're getting to date. And so our goal with the Crud challenge problem is to predict the Crud thickness, boron uptake, impact on core power distribution, and also cladding corrosion. And we'll go through that in a little bit more detail in a minute here. Let's see, advance. So I had already introduced our folks. Brian Kendrick will talk about the multi-scale aspects of Crud modeling, including the chemistry physics of Crud deposition onto fuel rods. Kevin Clarno will talk about the multiphysics aspects of the Crud challenge problem, including integration, neutronics, thermal-hydraulics, and Crud chemistry. And Jeff Secker, who's our challenge problem integrator for this challenge problem, will talk about, first give a background on the problem that we're solving, and then give some recent simulation results. So with that, I'll hand this over to Jeff Secker to introduce the Crud challenge problem. So Jeff, you're up.
All right, thanks, Jess. As just mentioned, what I'd like to do is just give you a little bit of background on what Crud is, and then I'll pass it on to the others to talk about modeling, then eventually I'll come back and show some of the results we got there as well. So the question is, what is Crud? You may not have heard too much about it. It's not something we often think of when we're designing fuel or reactor cores. But we do get deposition of some corrosion products on the fuel rod surfaces. We make all of the primary circuit out of highly corrosion resistant material. Typically it's stainless steel 304 for the piping and for the reactor internals, and it's nickel-based alloys for the steam generator tubes. As I mentioned, they're highly corrosion resistant, but some small amount of corrosion does occur, and a fraction of the material that does corrode does get released into the coolant itself and circulates around in the primary circuit. That then can become available to deposit on the cladding surfaces too. Crud deposition, and we just refer to the iron and nickel oxides that deposit on the zirconium-based cladding as crud. That crud deposition is strongly enhanced, though, if the core is undergoing subcool boiling. On our more recent PWR designs, we've tried to increase coolant temperatures so we can operate the plants efficiently, get more power out. Many of the operating pressurized water reactors have also undergone power uprates to increase the power output by 5% or more compared to the original design basis. And we also have some fairly aggressive fuel management in place, trying to get as much power out of as little uranium as we can put in there. The result of that is certainly pressurized water reactors operate below saturation temperatures for the bulk coolant. We never exceed saturation in normal operation. However, some of the cladding surfaces can be above saturation temperature during operation on the higher powered fuel assemblies and fuel rods. What that means is we then form steam bubbles on the fuel cladding surface. As soon as they move into the bulk coolant, they condense because the coolant is below saturation conditions. But that does provide a mechanism then to bring these circulating iron and nickel to the cladding surface. And once the steam bubble forms, any iron and nickel that was in that liquid water gets shed from the bubble and typically does deposit then on the fuel cladding surface. So that's crud. One of the things that we get concerned about is crud-induced power shift. Crud can cause some unexpected things to occur as far as depositing neutron absorbers in the porous crud layer, and that can result in an unexpected shift in power distribution. So what we refer to as crud-induced power shift is really an unexpected shift in axial power distribution, typically toward the bottom of the core or toward the core inlet. Subcool boiling is going to be most prevalent in the hot regions of the core, which is going to be upper spans, where the coolant's already heated up from the inlet, and again, cladding has gotten above saturation temperatures in some cases. So SIPs is certainly caused by crud deposition. Crud is typically a porous material. We're not just depositing an insulating layer. Coolant can still flow through the porous crud, and that porous crud does have steam chimneys also, which is typically where the vapor escapes from. That subcool boiling process, as I mentioned before, then does draw iron and nickel in toward the cladding surface and results in crud deposition there. As that crud gets thicker, and as we continue to have subcool boiling in the porous crud layer, we also now have a mechanism to concentrate any other impurities within that porous crud layer. So typically in an operating PWR, we're using boric acid for reactivity control, and that would result in a acidic type coolant, which can increase corrosion rates on system surfaces. So we do add lithium hydroxide as a buffer to maintain a near neutral pH in the presence of the boric acid. So when we have liquid containing boron and lithium, and it gets drawn into the porous crud by the subcool boiling process, that provides a way to concentrate boron and lithium in the crud, because the steam is going to exit the crud, but without taking appreciable boron or lithium with it. Boric acid is light volatility, not much, and lithium really isn't volatile at all. So that process then concentrates boron and lithium in the porous crud layer. And if we concentrate it to high enough levels, we deposit a lithium-boron compound in the crud. Typically, we expect that to be a lithium tetraborate type compound there. Boron is a neutron absorber, and we use it for activity control. We use it in control rods and other materials to control reactivity. So when we deposit boron in the upper spans of the core, that's going to shift the flux distribution away from that neutron absorber toward the core inlet. In PWRs, we have a term called axial offset, which is just a very gross measure of the axial power distribution. It's really defined as the power in the top half of the core minus the power in the bottom half of the core divided by the total core power. Pressurized water reactors operate with a negative moderator temperature coefficient, so the cooler, lower temperature zones tend to be a little bit more reactive, and as a result, axial offset in a PWR is typically slightly negative throughout the life of the cycle design there. With SIPs, and you can see in the figure there, the blue curve would be our predicted axial offset, again about -3% for the last 2/3 of the cycle. When we get crud deposition occurring, though, it takes some amount of time for the crud to get thick enough to actually result in precipitation of the lithium-boron compound. So you'll see in the first portion of the cycle in that example figure there, the measured and predicted axial offsets are in good agreement. Once we start to get thick crud deposits and boron deposition in the crud, though, you'll see that the measured power distribution gets skewed toward the core inlet a bit. Why do we care about that? Well, we like to accurately predict the evolution of the flux distribution and power distribution throughout the cycle. When we design a core, we want to know what to expect over the next 18 or 24 months of operation there. And certainly when we get crud and boron deposition, that causes an unexpected shift in flux distribution. So the core power distribution becomes somewhat unpredictable at that point, and that's not a situation reactor operators like to be in. It also alters core reactivity. Interestingly enough, these lithium-boron compounds have retrograde solubility. Typically things are more soluble at high temperature compared to low temperature. But lithium tetraborate goes the other way. It's actually more soluble at low temperature. So when we're operating the core at full power, we're depositing the lithium-boron compound there. But now if we reduce power, meaning we're also reducing coolant temperature, then the lithium-boron compound can dissolve back out of the crud. So now we've got core reactivity that's changing as we change power level. This can also then cause a loss in shutdown margin. Again, the deposited boron is present when we're operating at full power, but it dissolves following a reactor trip at 0 power. So it's almost like we're operating with a control rod in the core at full power. Then when we reduce power, we pull out that control rod, making the core more reactive. In the worst situation, and this happened in the Callaway plant back in around 1990, we had extreme enough SIPs that we were eroding shutdown margin and couldn't meet the current licensing requirements for shutdown margin. And that did cause the plant to have to operate at reduced power for about 11 months overall. The other effect on crud, if we do get thick enough, we have in a few cases led to fuel cladding failures. And that's what we refer to as Crud Induced Localized Corrosion. If we get sufficiently thick crud, we can impede heat transfer and then increase cladding corrosion there as well. One of the things I've been working on then with CASL is trying to establish SIPs modeling capability. So we can accurately predict crud deposition, we can accurately predict boron precipitation in the crud, and then also predict how that does affect the core power distribution, though. We use a variety of tools for that. Really, the SIPs challenge problem is really amenable to multiphysics type analysis because it involves neutronics, it involves thermal-hydraulics, it involves crud and chemistry as well. So we've linked all those codes together to provide a more accurate model of the SIPs process. So we're using a robust neutronics code to accurately predict the core power distribution and heat flux. That neutronics model, though, also has to be able to accept the fact that we do deposit crud and boron in the upper spans of the core. So we want to model the neutron absorbing effects of both crud and boron in that neutronics model as well. We need the thermal hydraulics model then to model local thermal conditions in the core, including the subcool boiling rates and distribution, since that'll govern crud deposition. Then we need a model to actually model crud deposition and how those deposits grow with time during plant operation. And in addition to that, we also need a chemistry model within the crud So we need to predict how boron and lithium get concentrated and when and how much lithium tetraborate forms. I think that's it for my introduction to CRUD. I'll pass this on to Brian Kendrick then to talk about some of the actual CRUD models he's developed.
Good. Brian, are you there?
Hello? Can you hear me?
We can hear you now.
Yeah, that's good.
Okay, so I'll continue with the CRUD modeling effort, in particular the code that we're calling MAMBA, which stands for FMC Advanced Model for Boron Analysis. And I'll talk a little bit about the development and some of its applications that we've been doing. Let's see. So in the FMC focus area, which stands for Fuels, Materials, and Chemistry, the goal here is to deliver engineering scale, fuel performance models, and materials physics-based constitutive models for CASL challenge problems. And in particular, the PCI pellet clad interaction challenge problem, the CRUD challenge problem, which stands for Chalk River Unidentified Deposit, and the GTRF grid to rod fretting challenge problem. And here I'll be focusing on the center box, the CRUD challenge problem. And the modeling approach that we take is a multi-scale approach depicted in the bottom two figures there, where we use atomistic as well as molecular-based and microscale transport models to determine some of the fundamental correlations and parameters that are then used in the engineering scale code MAMBA. And I'll talk a little bit more about that in detail as we move along. So this slide shows the MAMBA 3D computational grid, and I'll move from right to left in this slide. Over on the right-hand side is a cartoon of a reactor core, and as Jeff just mentioned, typically in the upper spans of the core where subcooled nuclear boiling is occurring, we have these CRUD deposits forming. And there in the center panel, you'll see a zoomed-in view of along a fuel rod. The CRUD deposit is exaggerated here. It's depicted in yellow between the two spacer grids. And within this deposit, you have these chimneys, boiling chimneys. The little round circles there represent the vapor bubbles that are forming. It's typically a nickel ferrite material. Porous material, has about a 0.7 porosity. There's other species such as nickel oxide and zirc oxide in the CRUD layer. If you look down at the bottom pictures, there's a top view of the CRUD layer, and you can clearly see the boiling chimneys and the porous nature of the CRUD. And over on the right-hand side, you see a side profile view of the CRUD layer. Again, you can see the vertical boiling chimneys and the different layers of the CRUD layer. On the left, middle left, is a view of the computational mesh that's used by MAMBA. So we grid up the CRUD layer. The vertical axis there is the axial height. The horizontal scale on that figure is the radial distance away from the cladding surface in microns. And that shows a picture of the CRUD, which corresponds to the yellow layer there in the middle figure. And as Jeff just mentioned, of course, we want to address the industrial relevant issues, namely the Crud Induced Power Shift, CIPS, and also the Crud Induced Localized Corrosion. So on this slide, I'm now going into more details about the computational approach that's used to model CRUD. So again, here's the grid. The radial deposition of CRUD is CRUD deposits on the surface. This is MAMBA uses an adaptive mesh or grid that grows as the CRUD layer grows. Also, this growth is determined by the temperature of the cladding surface as well as the concentrations of the particulates such as the nickel and iron that are in the coolant that come from the corrosion that Jeff mentioned previously elsewhere in the primary circuit. We also have erosion effects occurring due to the turbulent nature of the coolant flow around the spacer grids, for example, and I'll talk a little bit more about that later. So in order to compute the chemistry of CRUD deposition, we need to solve a heat transfer equation. And so we need the heat flux at the cladding surface depicted by the red arrows in the bottom there. And we also need the heat flux leaving the surface of the CRUD depicted by the red arrows on the top. Once we solve the heat transfer equation, we get the temperature distribution through the CRUD layer, and we can determine where the temperature is greater than the saturation temperature and the regions where boiling is occurring within the CRUD layer. And this boiling induces flow through the porous CRUD, and it draws in soluble boric acid, lithium hydroxide, as well as the nickel and the iron that are also in the coolant. And these species get concentrated near the cladding surface, and if they get a high enough concentration and the temperature is high enough, they can then precipitate out a solution and form a solid phase. And the threshold or solubility that for these different species is determined by thermodynamics models and chemokinetics models, which is computed in each of those regions that there on the mesh. So this slide shows, for example, the fundamental DFT-based free energies and thermodynamic correlations that we've been developing, and these have been incorporated into MAMA, these correlations. The top left figure there shows an equilibrium constant for LiBO2. We've also developed other solubility correlations for lithium tetraborate as well as boron cordite. And so these models are in MAMA. The bottom left figure shows the Crud porosity at 450 days in a simulation. And you can see near the cladding surface on the left there, the Z direction, the blue and green regions represent solid phases of lithium tetraborate, where it's precipitated and filled the pores of the crud layer. So it's no longer a porosity of 0.7, it's more like a porosity of 0.2. Over on the right there, it shows an integrated boron mass as a function of cycle time. And as the crud layer gets thick enough, it heats up, eventually you reach the solubility threshold, and suddenly lithium tetraborate starts to fill the pores of the crud layer. This slide gives kind of a high-level overview of the MAMBA development effort to address the crud challenge problem. So MAMBA is leveraging off of existing capabilities, namely the BOA code, which has been developed by Westinghouse and EPRI, and it's also leveraging off of a chemistry and particle transport code developed at Los Alamos in support of NNSA's stockpile stewardship program. The bottom orange boxes denote the different fundamental physics models that are going into MAMBA, namely a boron deposition model that's being developed at MIT, a nickel oxide model at NCSU, thermodynamics correlations at Oak Ridge and Los Alamos, as well as thermal conductivities and subcooled bowling models developed at Los Alamos, and also within the Athermal-hydraulics focus area in CASL. These models get integrated into MAMBA and then are used to predict crud deposition and evolution, and these are then benchmarked against available experimental data, including the Westinghouse Walt loop circuit, as well as operating plant data. And I'll present some examples of that next. So these are some highlights of the MAMBA development and applications and validation. Starting at the top, we did an initial MAMBA coupled to a CFD code star CCM plus and neutronics code Descartes, and looked at an initially a single pin cell geometry. It's depicted up on the right there on that little picture. And this has appeared in the Annals of Nuclear Energy. Then we then extended that to 4x4 subassembly. And along the way, we also did initial validation and benchmark studies against the Walt loop experiment that I just mentioned, as well as BOA. And some of these studies led to improved boiling models in industry's BOA version 3.1 code. We extended the modeling effort to a 4x4 subassembly, and then eventually to a 5x5 subassembly, and applied it to an operating PWR, namely Seabrook Unit 1 of Cycle 5. And I'll present some more results on that in more detail. Later today, in the following presentations, this past year, we've coupled MAMBA to IMPACT as well as CTF, and have done a full quarter core simulation of Watts Bar Unit 1 Cycle 7.
Are you there, Brian? This is Jess. Did we lose Brian? Is anybody else there? Jeff, can you hear me?
I can hear you, Jess.
Okay. Well, we lost Brian. Jeff, are you there? Okay. Well, maybe I can talk about these slides a little bit. What you should be seeing now is an animation video show the crud growth on a single rod. Let's see. Silence. I'm just watching the chats here. So, is there, Nicholas, are you on, or Natalie? Can you hear me? Okay, Jeff can hear me. Jeff, we can't hear you.
Yeah, sorry, I was on mute earlier while I was talking. So,
what I'm hoping is, since we lost Brian, maybe you can talk about some of the results that are here, because you're probably most familiar with it.
Yeah, I can do that.
Let's hit play on these videos here.
All right, yeah, this was just, again, as Brian mentioned, some of the crud simulations we were doing early on. In this case, it was just a small segment of an assembly, so just a 4x4 rod array. One of the models we did set up, though, was in Seabrook Cycle 5, they experienced both crud-induced power shift and crud-induced localized corrosion. So we did some modeling for that on one of the assemblies that did have both the fuel failures and the boron deposition. So that was just, at the time, we didn't model the full assembly, we just modeled a 5x5 rod array. And this was done using computational fluid dynamics as a thermal-hydraulics model, so we could see very localized variation in the thermal conditions around a fuel rod, and then using the 3D Mamba code for the crud and chemistry simulation. This was done a couple of years ago. At that time, we just used input power distributions rather than driving them from the neutronics code itself. So this was really just a coupling of the thermal hydraulics and the crud and chemistry code. But we could see both the axial and the azimuthal variation in crud deposition, which is very similar to the observed crud we could see on the Seabrook fuel assemblies when we did the examinations there. This just provides then a profile of the crud layer on an individual fuel pin there for one of the fuel rods in that 25 rod simulation. We did have crud scrapes from Seabrook, and the actual crud thickness was approximately 80 microns thick on some of the thickest crud we found, or a little over 3 mils. The plots there you see are the different crud parameters, porosity on the left side, temperature within the crud deposits as the second figure from the left, the subcool boiling heat flux, the third figure from the left, and then the boron deposition in that crud layer on the rightmost figure. We also then had some comparisons when we did have the fuel failures. Of course, then we go in and do examinations on the fuel itself. So we'd measured the combined thickness of the corrosion layer on the cladding surface and the crud deposition on top of that corrosion layer. And that is the black curves you see on this particular figure. We then compared that to the Mamba prediction, which is the green figure there. And you see we're in pretty good agreement as far as the axial distribution of crud. Now, again, the black would be a combination of the clad corrosion or clad oxide thickness and crud on top of that. In Mamba, we're not predicting that clad oxide corrosion layer thickness. So that's why the peak values measured are greater than the predictions there. But you see, axially, we predict it in the right locations and about the right magnitude as well.
Okay, looks like the video killed my connection, but in summary, we reviewed the crud modeling framework or MAMA development within CASL, namely the crud growth, including the erosion, heat transfer, including chimney boiling, soluble transport due to convective boiling-induced Darcy flow, as well as diffusion. I also talked about the thermodynamic models, which includes boric acid chemistry. We also include microstructure models, namely the porosity and and the change in porosity over time, as well as coupling to external CFD codes and neutronics codes. Also presented some simulation results for the single-pin Descartes simulation that was star CCM+, also a 4x4 preliminary demonstration calculation, and then on to the Seabrook's Unit 1 PWR, and then Jeff finished with the description of the results there. And then the rest of the presentations will discuss our recent results using a Mamba subgrid module that we developed recently to model a full quarter core simulation of Watts Bar Unit 1, Cycle 7.
Okay, I've got a question, a particular chemistry question, so maybe we'll ask this one now since it's so specific. And basically the question is, in the past, particularly in BWRs, crud formation was highly dependent on water chemistry problems, particularly copper and similar elements in the coolant. The question is, do we see effects of other elements on these crud deposition mechanisms? And either for Brian or maybe Jeff might be familiar with this. Is it primarily the nickel and iron, or do we see any other elements contributing?
Yeah, I can address that. In PWRs, it's primarily the nickel and iron. We do get some other small contributions when we do crud scrapes and do the chemical analysis of the crud, but 98% plus is generally iron and nickel. You're absolutely right, though, in BWRs, the crud there is slightly different because the water chemistry in a BWR is more of an oxidizing type environment. They still get primarily iron-based crud, but as you pointed out, also any other impurities like copper from some of the condensers or others than that, and it's caused particular troubles with BWRs as far as fuel performance. They have had fuel failures because of the copper-heavy crud deposited on the rod that tends not to be very porous, unlike PWR-type crud. But if we added, we could certainly add that capability into Mamba to model other elements as well. For PWRs, we just haven't had to do that. So.
All right, very good. Okay, so we'll continue. Kevin Clarno is up next, talking about the physics integration. So Kevin, you're up.
So in the physics integration focus area, we are drawing from the other focus areas like FMC and pulling in those codes and capabilities developed there to integrate them and provide them to be able to be used by industry as well as solve the challenge problems that Jess has mentioned. And so this is a very big effort that incorporates all of the different partners. And so a whole lot of people have contributed to this. I just get to be the one standing up presenting it. So as an outline, I'm going to talk about the VERA, which is the Virtual Environment for Reactor Analysis, and focus primarily on our ability to predict normal operation with what we consider modest computing resources. In industry, when or the regulator where a single processor or a small workstation is normal computing power, and at some of the national laboratories where we have supercomputers can span hundreds of thousands of processors. We wanted to make sure that we were developing a tool that was usable on a few thousand processors operating within a day or so. I'm going to talk about some of the multi-scale challenges that we face and go into detail on this particular CRUD application. I'm going to go over some of the validation work we did modeling Watts Bar Unit 1, 12 cycles of it, discussing some of the results and limitations and why it was a great case for extending the coupling with Mamba for CRUD analysis. So VERA is really a collection of codes. It covers all the physics that we tend to model in a nuclear reactor, neutronics, thermal-hydraulics, fuel performance, chemistry. It covers a breadth of scales. For example, we have continuous energy Monte Carlo transport and deterministic transport. With Cobra TF, we have sub-channel thermal-hydraulics, but we also have both industry CFD codes and the Hydra TH CFD capability. With fuel performance, there's really only one code. It's the Bison code, but there are fuel models inside of Cobra TF. And so we can span these different scales. Some of these different codes are coupled. So there are also a lot of tools that really enable coupling. But all of these things really leverage common infrastructure to simplify their use and development. Let's see. All right. So focusing on the application of VERA for core simulation, what we are really doing is we're taking the impact neutronics code, the deterministic neutronics code, and the Cobra TF subchannel thermal-hydraulics code, and just modeling nominal operations, so quasi-static neutronics, steady-state coolant flow, simplified pin heat transfer. Putting this together with a full capability to rotate and shuffle fuel and deplete over multiple cycles, we can produce a full span of high-resolution results that we're able to compare with zero-power physics tests and boron letdown curves and in-core flux detectors to evaluate the quality of our results. We also can compare with the actual plant operational data. And so what you see here in the top right is cycle 1 of Watts bar, cycle 7 of Watts bar unit 1, some of the results that we have. Oh, got some. So these tools, as I mentioned before, we're really focused on making things easy to use. So we have a single input, single output capability, and we're focused on what we consider to be modest computing resources that could be accessible to industry, even if it's not what they're generally used to using today. So the impact integrated neutronics code is providing pin-resolved neutronics. It incorporates on-the-fly cross-section processing, full core radiation transport, isotopic depletion and decay using the origin depletion code. The 3D pin-resolved transport uses the 2D 1D method, which is 2D radial method of characteristics. So at every axial plane, it does 2D ray tracing across it, accounting for all of the physics that you'd normally see in a lattice physics code, but spanning the whole core. And it links those axial planes together with a 1D SN or SPN transport-based solution. Instead of in a traditional core simulation where you'd have a lattice physics step modeling the 2D transport on a single assembly and homogenizing and smearing all of the materials and doing your full core analysis on 2 or 4 energy groups, this is doing the full transport on 47 energy groups. And to be able to get a reasonable solution, this scales very well out to tens of thousands of processors. So that we can produce results in a reasonable time. There's been a lot of validation work in process. We have compared with quite a few critical experiment benchmarks. We've done comparisons with plant data, and we do comparisons with the continuous energy Monte Carlo codes, MCMP, Shift, and Kino as well. Cobra TF is channel resolved heat transfer. It is providing the full integrated heat transfer solution. So it is doing radial heat transfer within each pin. It's doing thermal hydraulics throughout the core, modeling the 2-fluid, 3-field model. So it's modeling the fluid, the vapor, and the droplets. And it can operate in static or transient mode. What this provides is this allows us to resolve the flow in every individual channel in between fuel pins. And in the heat transfer, it's modeling each quadrant in every single pin cell. And so that winds up, when we're thinking about CRUD and modeling CRUD, we wound up for a full core calculation having 30 million individual clad surfaces in the core. So to allow this to run in a reasonable time, we parallelized it as well. So it runs, scales well out to hundreds of processors, and that we're going to continue to push on and improve. And the validation of Cobra TF is in progress, but it has a long history, so it is relatively well qualified. But we've done quite a few single and two-phase benchmarks and comparisons with CFD. So in the past, one of the partners for CASL is TVA, and TVA Watts Bar Nuclear 1 has primarily had Westinghouse Fuel, which is another partner. So we use the Watts Bar Nuclear Unit 1, cycles 1 to 12, as a excellent tool to compare our results against. So Watts Bar 1 is operated by TVA. It's a 4-loop Westinghouse PWR, operating from 1996 till today, and it's currently in its 13th cycle. Unit 2 is going to start up this spring, so that's good for the whole industry. So for every single cycle, at every single state point, we have at every single state point that they evaluated the flux maps. What we have is we have a 3D evaluated estimates of the flux distribution throughout the core. In this plot, you see a quarter of the core. The blue and red, what look like lines, are actually comparisons of the computed solution in blue and the measured solution as red dots. And so for every single assembly where there's a flux detector, we're able to pull off what is both the comparison of the measurements and the experiments, and we can get in the bottom right corner of each of those boxes, the assembly average flux comparison, and the root mean square of the individual axially varying is in the top right corner. And so pulling all that together in the bottom right, you see a core average, so we can compare the full core average axial distribution, and we can evaluate for every single cycle that we're modeling, how do these results compare with the measured data. And we can bring all of that together and look at cycle by cycle comparisons. And the top left, there's a table that has cycles 1 to 12, how many different detector counts were recorded, what's the change in the axial offset between the measurement and the experiment. What is the 1D, so the axially integrated core average, root mean squared error, the 2D, so the assembly average root mean square, and then the individual 3D, looking at the maximums and other areas to really see how these various cycles were performing. In general, in the bottom left, you can see the assembly average values. Generally, we're in the few percent range error. There weren't too many big anomalies. But in the top right, we're looking at the axial offset. As Jeff mentioned, the axial offset is the ratio of the top to bottom power distribution. And you can see that there was one cycle that was really unusual, and that was cycle 7. Cycle 7 in Watts Bar 1 experienced some significant SIPs. And as you can see, our simulation of that, since it didn't include any Mamba calculations, was pretty significantly off, despite the fact that on the other cycles it was pretty good. So Crud is a very localized deposit. As has been mentioned previously, this isn't something that you see on in very big, large regions. So to really evaluate that fine mesh resolution, we have integrated Mamba with both the Hydra TH as was shown earlier, and the Star CCM, so we can get CFD coupled with Mamba results to understand that distribution on the surface of the cladding. And so what you see here in the right is just a single rod with a grid spacer that you'll see down about 15–20% of the way up from the bottom, and the flow is going up, and so the variations that you see when you're modeling this with CFD is you start to see flow variations that lead to temperature variations on the clad surface. That variation is really azimuthally changing around the pin. And so due to that azimuthal temperature variation, you have crud growing in the hottest regions of that channel. And so that crud is building up and getting thicker. And that crud impedes heat transfer. And so that increases the clad surface temperatures and affects your the temperature in your fuel. And as mentioned earlier, as that builds up, you get more and more boron that starts to deposit on the fuel, on the surface of the cladding in those crud regions. As you can see, that there is quite a bit of azimuthal variation that is in here. And while Cobra TF is high resolution compared to what traditional core simulators use, where you'd have flow in a full assembly or a quarter of assembly all averaged together, Cobra TF modeling every single channel is significantly more resolved. It still isn't able to pick up these azimuthal variations. So we're able to use CFD coupled with Mamba to really understand and refine how to get the integrated Cobra TF plus Mamba solution to provide the right answer that would replicate what you'd see in Cobra TF. So for modeling SIPs, it became clear that we needed to incorporate Mamba with the impact in Cobra TF. And so in that core simulator, we extended it for SIPs analysis, where Mamba is passing how much crud is growing, the thermal resistance from the crud, which affects the heat transfer between the fuel and the coolant in CTF, and the crud thickness and mass and the boron mass, which impact is affecting the cross sections used in impact. And impact is passing the coolant boron concentration, and Cobra TF is passing all of the coolant and surface temperature information to Mamba. And so getting all of those things linked and worked together provided us with the capability to really understand how well we are able to account for this crud growth in cycle 7 for watts bar. And the details of that I'm going to leave for Jeff to talk about in just a minute to sort of discuss how well that went. So in conclusion, VERA is the suite of tools for high resolution analysis of reactors and fuels. VERA couples many of those tools in a variety of ways to enable a prediction of reactor performance and analyze both nominal operation and many of our challenge problems. The crud-induced power shift directly depends on many of these local quantities, subcooled boiling, for instance. But these quantities are very globally dependent, such as the power distribution. So they have to be modeled both at a very fine local level, as well as the full reactor multi-cycle distribution. So we have to account for this azimuthal variation of the crud growth in the rods, even though CTF can't predict it. And so that means we have to work with CFD to do that. And we have to be able to model many cycles of this as it grows on the fuel. And so we talked about the application of VERA for cycles 1 to 12 of watts bar unit 1, demonstrating that the accuracy of VERA through many of those cycles, but really highlighting the limitations that neglecting crud can have in some of the cycles where there were problems. By doing so and incorporating Mamba, we dramatically improved the VERA solution in cycle 7. So many of these multi-scale physics integration challenges remain for the other challenge problems, and continued work is ongoing with regard to the crud modeling of this multi-scale problem.
Thanks, Kevin. I'll go ahead and go through the results of our modeling then. Again, as Kevin mentioned, Watts-Bar Unit 1 Cycle 7 did experience SIPs during that cycle. The previous cycles had not had any of those indications. What you'll see here, the red curve is just the blue curve is our original design prediction back from around 2004. And that's with Westinghouse Advanced Nodal Code. So this is a two-group nodal code-based method that we use for standard design applications. You'll see the red curve is the actual measured values there. And you see we didn't do a great job predicting axial offset early on with the simple codes we were using. The measured values were certainly more positive than predicted. But what you do see is after about 5 months of operation, or a cycle burnup of 6,000 megawatt days per metric ton, you do see this rapid drop in axial offset occurring. And that was a result of crud deposition and then boron deposition into crud. You'll also see a couple of transient effects there. There was a power reduction around 6,000 megawatt days per ton. As I mentioned, what happens there is that as the power goes down, then the boron compound dissolves back out of the crud. It's been sitting in a neutron flux for a while, so it's partially depleted in boron-10, the neutron absorber. When it dissolves out, and then when you return to power, it reprecipitates. But now it has a higher boron-10 content, corresponding to what was in the coolant of boron-10. So you'll see that step change there after the power reduction, which is still expecting to have the same mass of boron in the crud. It just has a little bit more boron-10 in it now. Likewise, around 13,000 megawatt days per ton, there's a second power reduction. You see that same effect occurring there. But clearly, after 6,000 megawatt days per ton, SIPs was occurring throughout that cycle. They had another exciting event then late in the cycle, just after 16,000 megawatt days per ton. They actually had an issue with the turbine blade. They threw a turbine blade there, which forced them to shut down to make the repairs for that. During that time, they went to cold depressurized conditions and added a lot of boric acid to the coolant to keep the core subcritical. And we were down there for almost 3 weeks. That actually resulted in dissolution of a fair amount of the crud that had been deposited on the core. So when they restarted, they had much thinner crud, and as a result, they didn't precipitate boron in the crud anymore. And you see that large positive shift in axial offset. So from 6,000 to 16,000, they were depositing boron. You're seeing the more negative axial offset. At 16,000 megawatt days per ton, they removed some crud, no longer precipitated boron, and you got that large increase. We did simulations then with the three coupled codes that Brian and Kevin had talked about. So the impact transport neutronics, the CTF, subchannel thermal hydraulics, and the Mamba crud and chemistry code. You'll see the left figure is just a predicted power distribution. This is right before that turbine blade shutdown there. So prior to that, you can see the power distribution on the left side. The red is the hottest assemblies. Typically, those are the fresh assemblies. If you look to the right there, you'll see that the corresponding crud deposition occurs in those higher powered assemblies. So those are the ones that are going to have subcooled boiling, typically only in the upper half of the core, and that's where you see the crud distribution in that right figure there. Then we also predict the boron deposition, though, at that same time step. You see that gray type material is the predicted boron deposition there too. So we are able to predict boron in the upper spans. That again corresponds to the thick crud deposits as well. Where you see thick crud, you'll also see the boron deposition. And the next one shows the axial offset behavior. The prediction there for the, I guess that's a purple curve with X's in it, is really the standard impact CTF prediction without modeling crud. So you can see early in the cycle, axial offsets predicted pretty well, consistent with measurement. But then in the middle of the cycle, the measured values, again, were more negative because the core was experiencing SIPs. So those green triangles are the measured data. Again, you can see that the jump in the axial offset late in the cycle after they removed a bunch of crud during that 3-week shutdown. When we simulate this with the linked impact CTF Mamba codes, though, you can see we are able to predict then the crud deposition that occurs and the resulting crud-induced power shift as well. Now, this model currently doesn't contain the boron 10 depletion effect in the crud itself. So we don't capture that significant 2% step down at 6,000 megawatt days per ton, or the corresponding one that occurred around 12,000, 13,000 megawatt days per ton, simply because we haven't included that in the model yet. We intend to, and that's under development, so we'll have that pretty soon as well. But you can also see then we did simulate the removal of crud there, and we match that big jump in axial offset around 16,000 megawatt days per metric ton as well. So overall, this is quite a good result in terms of trying to simulate cycle 7 of WattSpar Unit 1. Provide a little bit more information also, as Kevin had talked about. When we did the simulation simply with the impact CTF linkage without modeling crud, clearly in cycle 7 we saw some substantial differences in axial power distribution because SIPs was actually occurring there, but we weren't modeling the effects of that. When we include the effect of SIPs by adding Mamba to the simulation, you can see we get much, much better agreement in axial power distribution throughout the core. So some of the previous deviations in the upper spans that we were seeing aren't present anymore because we are now modeling what actually occurred, the actual boron deposition in the crud that did result in that power distribution shift. So just to summarize our initial SIPs modeling, we're quite pleased with these results so far. This is the first time we've been able to do a full quarter core simulation of crud with the CASL tools. As Brian Kendrick had mentioned, we'd had several other multi-rod simulations or even up to a full fuel assembly. But this is the first time we've done a whole quarter core simulation for an actual core that did experience SIPs. So we took the multiphysics tools that CASL had developed and did apply those to WattSpar to model crud deposition on the core and the resulting effect on core power distribution. The pin resolve 3D transport neutronics, which is the impact code, again, it's been coupled with the subchannel thermal-hydraulics, the CTF code, and the crud and chemistry models, the Mamba code there, really to create a true multiphysics crud modeling and simulation tool. We did apply that to WattSpar Unit 1 Cycle 7, and we're able to simulate the actual SIPs behavior pretty well, actually. Really a great result for the first time attempt at the simulation of that. We do have some future things we need to improve there. Some additional improvements to the models are planned and underway, some of the like B10 depletion effect I mentioned. But we've come quite far in the first 5 years of CASL as well, and are actually now really getting to the point where we can do some pretty accurate SIP simulations. Again, our long-term hope is that we'll be able to use these tools then to also find out ways to avoid crud deposition in the future. So future cores should not have thick crud deposits and hopefully will not experience SIPs or silk in those. If these modeling tools are robust, we can look at, like I said, the solutions to the crud. How do we prevent it from depositing? How do we make sure we never get thick crud deposits and never have to experience SIPs or silk?
Okay, this is Jess again. So that concludes our presentation. We're available for questions, and there are a few questions on here if you're following the questions, but I'll go through a few of these. So we did get a question about runtime. Maybe Kevin can talk a little bit about runtime and the computers that we run on.
Yeah, so the our target that we are working towards is really 1,000 processors and less than a day. Right now we're a little under 4,000 processors generally. This is for a quarter core simulation, and we're about 18 hours for a single cycle. Adding Mamba really did not add much at all as far as computational burden. We had to do some work to make sure that we understood the coupling and minimize the memory and the constraints. But in general, adding that component really didn't affect the runtime at all. The computers that we run on, so we have the big machine at Oak Ridge is a couple 100,000 processors type, and we generally don't use that very much. It's really designed for very big capability type of computing. We have a smaller machine, EOS, and then the Office of Nuclear Energy has two machines out at Idaho, Fission and Falcon. And they're both very effective machines that we've been able to get a lot of throughput. They're really designed for running a lot of problems in the 4,000 to 16,000 processor range.
All right, thank you, Kevin. We've got a question about if Watts Bar is using these codes yet to model their plant operation. And I'll answer that. So TBA, we have TBA staff that's working with us, but these codes are not used for actual core design or core follow yet. We're still establishing the accuracy basis, as you saw with the 12 cycles, and pushing forward on the challenge problem integration. We generally don't see these as codes used for standard core design because of some of the run times that Kevin just talked about are probably too long for that, but they're good for investigations as well as looking at details into the challenge problems and for confirming results with other codes. So that's my answer to that one.
Yeah, I guess one additional thing I can add too is for Watts Bar Unit 2, we do actually plan to do some simulations with impact prior to the startup there, just to confirm that our design predictions using our standard license codes are expected to be reasonably accurate. So the CASL tools are not licensed by the NRC yet at this point, so we can't do licensing type calculations with them yet. But hopefully that'll come in the future. And as just mentioned, we can do confirmatory calculations or check calculations to make sure we're trying to accurately model things.
Right. Another question that came in was about how the assembly inlet flow was modeled. Maybe Jeff, you might be most familiar with that. If it's uniform, or do we have a distribution we use?
Yeah, for this currently we use a uniform model. Actually, we do expect to see a variation in inlet flow distribution just because of reactor lower internals effects. And we have modeled that in CASL with some of the computational fluid dynamics tools. That's not really cycle dependent or fuel dependent or core dependent calculation. It's really more just lower internals geometry. So we think we can use a computational fluid dynamics model to see what the actual inlet flow distribution is, and then start to use that in the impact tools as well.
Okay. While we're on the CRUD topic, we got a question about, have we studied CRUD deposition in natural circulation like SMRs, where subcooled boiling may be more prevalent than or circulation? So let me talk a little bit about that. So we are working in our second 5-year phase to look at small modular reactors which have natural circulation, but we've not modeled CRUD deposition yet. These results that we're showing you here for Watts Bar are about a month and a half old, so you're seeing some really current stuff. We do plan to go into this area though, so it's a very good question. Looking at some of the other capabilities, we've got a question about whether CASL codes, VERA, could be used for transient or accident scenarios, or is it appropriate for specific applications such as CRUD simulations only? So maybe, Kevin, would you like to answer that?
Yeah, so there are several transient challenge problems that we're going to be working on in phase 2. And so we're starting to work in that direction for a couple of them. The Bison Fuel Performance Code is transient and has been used for a variety of transient problems. But it really just in a standalone mode. The impact radiation transport is in the process of being extended for transients. Really sort of the target for a lot of that is modeling reactivity insertion accident capability really at the fuel performance level. And so we aren't yet, the plans in CASL aren't to have a full transient capability for full core simulation like you'd see with a RELAP 5 3D or something like that. But really just sort of targeted specific transient and accident situations.
Okay, thank you. We got two related questions here, so I'll combine these maybe for Jeff Secker to talk about using tools for new fuel design. Specifically, a more specific question is, are we able to model SIPs accurately enough so that the CASL tools can explore different designs to inhibit SIPs? What type of computing power resolution would be needed for that type of prediction? So, Jeff, maybe you could take a shot, and then on the computing power, if there's a different answer than we had before, maybe you or Kevin can comment.
All right, yeah, as far as new fuel designs go, yes, we're very interested in using them as we explore new fuel designs, such as accident-tolerant fuel, whether that's changes to the cladding material or the fuel pellet material. The code is certainly capable of modeling those. So one of the things Westinghouse was certainly interested in joining the CASL consortium was being able to obtain tools like this that can be used for future new and improved designs.
All right, very good. Kevin, any comment on the computing power, or do you see this similar to what we've already been talking about?
Yeah, I think it's similar to what we're talking about. I think as you start exploring more and more things, you'd really like something that ran faster. But if you have the computing powers, you certainly could use it for that.
Okay. We've got a question on experimental validation, particularly on thermal-hydraulics, and the question is, would experimental validation beyond comparing velocity and temperature profiles be useful? For example, measurements of nucleation site density, bubble departure diameters, local heat flux distributions, dry out area be useful. So I'll answer this at a high level. We have a thermal-hydraulics methods focus area that's looking a lot at multi-phase flow and modeling it and developing improved closure models for CFD. And we have some both computation and experimental work going on these sorts of parameters. So sources of validation data and to validate those closure models in our simulations is always very useful. Particularly, we didn't talk much about multi-phase here on this webinar, but we are working in that area. So that would be good data. Any good data we can get will be useful, and it's always hard to find. A couple more questions. How are multi-cycle effects being addressed? Example, over or under depletion of burnable absorbers in U-235 due to borated crud in the prior cycle. Jeff, maybe you can talk about this specifically, cycle 8 and then Watts bar and some of the impacts there, if you recall those.
Sure. Yeah. Like the initial simulations that were done for Watts bar cycles 1 through 12 didn't model effects like crud, and Kevin talked about that. However, once we started modeling crud in there, then we can use these tools to account for the differences in fuel depletion and in burnable absorber depletion and things like that resulting from SIPs. So we did take for this simulation where I showed you the cycle 7 results, we actually started in cycle 5, modeling crud and boron, carrying that into cycle 6 and then into cycle 7 as well. One of the things we'd seen in the initial no crud simulation, though, was for cycle 7, again, we weren't matching axial power distribution or axial offset well because of the effect of SIPs. But then also at the beginning of cycle 8, we clearly did see the carryover effect from the cycle 7 operation in the cycle 8 startup physics testing results, for example. So while we predicted things pretty accurately for most of the Watts-bar cycles, with the no crud simulation, clearly cycle 7 and its effect on cycle 8 didn't do all that well on the initial simulation without crud. When we did model cycle 7 crud and SIPs and then shuffled that into cycle 8, we did get much better results for the startup physics testing as well. So we can see the multi-cycle effects using these CASL tools.
Very good. A couple more questions. Kevin, this one's for you. A specific question, will relapse 7 be included in the VERA package? So maybe talk about our systems model, interoperability, and relapse 7 specifically.
So relapse 7 will not be in the phase 2 plan. I believe for the transient analysis, we're talking about using the Westinghouse capability just to provide boundary conditions for the transient challenge problems.
Yeah. We have, this is Jeff, so we have, if you recall the VERA diagram, I could probably pull it up. CASL itself is not working with the system level simulator. We're relying on other developed simulators. I think relapse 7, if those of you are familiar with it, is being developed by INL. I would not rule out as it becomes available of something we could work with, but not our immediate plans are not to work with that. We're letting it mature till we're ready to integrate. A specific CRUD model question maybe for Brian Kendrick. How do you model CRUD substances physical transport from the bulk liquid to headed into the CRUD buildup? So Brian, maybe a short answer, if you can, a short answer to that.
Yeah, so the CRUD deposition rate or the growth of the CRUD, it depends on the concentration of these particulates in the coolant. And so but we model that by using the boiling rate or the mass evaporation rate at the surface, the cladding surface or in the CRUD layer. And so the buildup, the rate of buildup is proportional to the boiling rate. And so it's a parameterized model that captures that effect.
All right, and if you're interested, there's more details. If you contact us, we can get you more information. We got a high-level question. Does CASL expect to have these tools approved by the NRC at some point in time in the future? Is that part of the plan? So CASL is not a plant operator. We're not a licensee. So we would not license or submit any sort of topical reports to the NRC. We would leave that to the potential end users. It could be a vendor or utility. What we're trying to focus on when we do our development is to make sure we have our capabilities in place that would enable that. Includes documentation. We have a QA plan that we follow, and so while we wouldn't ourselves take this through NRC approval, somebody may want to in the future. We don't want to preclude that. As far as the NRC, we meet with them and talk with them about what we're doing. At this point, we're a research program. We interact with the NRC Office of Research to inform them. We're well aware. I think that's been very, very useful so they can keep up with our research. We did get a question about the material. So the slides, you can see a URL there, www.casl.gov. That's our website. We'll make these slides available there. ANS, Nick or Natalie may want to comment on what's going to be available from ANS, but we'll have these slides available as well. With that, I don't see any further questions. I'm trying to make sure I didn't miss any, but I think that was it. So maybe I can hand this back to Nicholas at this point.
Hi, so thank you very much, Jeff, for organizing all this. So I don't think we have any more questions. I think this webinar will be available online, and so if the presentation also available on your website, that would be perfect. So with this, I will close this webinar. Thank you very much, everyone, for attending, and thank you for all the panelists, and again for Jeff and the ANS for hosting this webinar. So hopefully we'll organize, the young member group will organize another one in the near future. We'll keep you updated. Thank you again, and have a great end of the day. Bye.
All right. Thank you, everyone.
Thanks a lot.